In this video, we will be looking at the trigonometric substitution. So basically, as the name suggests here, is that this is about evaluating integrals by substituting a trig function. So let's say that usually the idea for this is that by substituting a trig function, the goal here is to get rid of the square root. So for example, if I have whenever I have an expression that looks like the root of some number a squared minus x squared, so a could be here 2 or 3 or some other number. So if I have an expression like root of a squared minus x squared in the integrand, then the substitution that's going to get rid of the root here is x is equal to a sine theta, where theta is between negative pi over 2 and pi over 2. And the reason we make this restriction on the domain of sine is so that we can use the inverse of the sine function. So when we make this substitution, one of the identities that we have to apply is this one that says that 1 minus sine squared of theta is equal to cosine squared of theta. Now, if we have an expression in the integrand, if we have an expression like this one here, root of a squared plus x squared, then the substitution that we would make is x is equal to a tangent of theta. Again, theta here is restricted to be between negative pi over 2 and pi over 2, so that we can use the inverse of the tangent function. And the identity that we need to use when we make this substitution is 1 plus tangent squared of theta is equal to secant squared of theta. And lastly, if I have a factor root of x squared minus a squared in the integrand, then we would take x to be a secant of theta. In this case, theta is restricted to be in the interval from 0 to pi over 2 or from pi to 3 pi over 2. And recall that this is the domain that we picked for secant to define its inverse function. And the identity that we're going to use here is secant squared of theta minus 1 is tangent squared of theta. Again, the goal is that by making one of these substitutions, we will uproot the root. So here is an example. So let's say I have the integral of root of 4 minus x squared dx. So here we will make the substitution x is equal to 2 sine theta. Well, then dx, right, the differential of x would be 2 times the derivative of sine theta, which is cosine theta, times d theta. All right, so we can see that we can replace dx by 2 cosine theta d theta, and then x will be replaced by 2 sine theta. So let's make the substitution. So x is 2 sine theta, and then dx is 2 cosine theta d theta. So the next thing we want to do is simplify this. 2 sine theta is the same as 4 sine squared of theta, and then we factor out the 4. So now we factor out the 4, and if we factor out the 4 here, we get 4 times 1 minus sine squared of theta. And recall that I said we have to use an identity. So the identity is 1 minus sine squared of theta is the same as cosine squared of theta. And so we get here root of 4 times root of cosine squared of theta times 2 cosine theta d theta. Now root of 4 is 2, and the root of cosine squared of theta is absolute value of cosine theta. So we still have the 2 cosine theta d theta here, and the absolute value of cosine theta here is the same as cosine theta because we have restricted. So when we make this sign substitution, recall that when we make the sign substitution, we are assuming theta is in the first or the fourth quadrant, so where cosine is positive. So as a result, the absolute value of cosine theta would be just same as cosine theta because cosine theta is non-negative here, so non-negative. And so now we get 2 times 2 is 4, which I'm going to take outside of the integral, and then we get cosine squared of theta. And now how do we integrate cosine squared of theta? Well, we apply the double angle formula here. So cosine squared of theta is half 1 plus cosine of 2 theta. And so half and the 4 will give me a 2. And then in the integrand now I have 1 plus cosine 2 theta. Okay, the integral of 1 d theta is just theta, and the integral of cosine 2 theta would be half of sine 2 theta. Okay, so the integral of cosine 2 theta is half sine of 2 theta. If you are not sure why that's the case, if you are doing the integral of cosine 2 theta, so what you could do is you can take u to be 2 theta, and then du would be 2 d theta. And so if you make the substitution, what you get is cosine of u, and then d theta would be half of du. So you get half integral of cosine of u du, and then you get half of integral of cosine of u is sine of u, and then I'm not going to write the plus c, and then we'll be replacing u with 2 theta. Okay, so that's why we're getting half of sine 2 theta when we for the indefinite integral of cosine 2 theta. Okay, so then we have this here. So now I multiply by the 2, so I get 2 theta, and sine 2 theta when I multiply by 2. Now I have the 2 theta. So remember that we made a substitution, and this is an indefinite integral, so I need to go back to x. And to go back to x, well, the first thing I'm going to do is sine 2 theta. I'm going to rewrite that as 2 sine theta cosine theta. That's an identity from the trigonometry. And okay, so we know that sine. So let's go back here. The substitution that we made was that x is 2 sine theta. So what is sine theta? Well, sine theta would be x over 2. So notice that sine theta is x over 2. So what is theta? Well, theta would be a sine inverse of x over 2. So I'm replacing theta by sine inverse of x over 2 because sine theta is x over 2. So theta would be sine inverse of x over 2. Now also, sine theta is opposite over the hypotenuse. So if I draw a right triangle and I pick one of these angles to be theta here, then because sine theta is x over 2, then I can pick the opposite to be x, and I can pick the I can pick the hypotenuse to be 2. So x over 2, x would be the opposite, 2 would be the hypotenuse. So what's the other side? Well, by using Pythagoras' theorem, the other side would be the root of square of the hypotenuse minus the square of the opposite, so that the adjacent would be this. So now I have 2 sine theta, so sine theta is x over 2, so that's sine theta is x over 2. And cosine theta, well, cosine theta would be adjacent over the hypotenuse, so I get root of 4 minus x squared over 2. So let's clean this up. So I get 2 sine inverse of x over 2 plus here 2 and 2 cancels out, but I still have a half. So half x root of 4x squared, 4 minus x squared. So that's it, the simplification, and then plus the c at the end because we were finding an antiderivative. So the idea here that we have used to evaluate cosine theta, for example, we have seen that when we talked about the inverse trig functions. Okay, so that's the answer for this integral. So notice that how we substituted 2 sine theta for x, and then at the end we were able to get rid of the root completely. So when we came to this point here, there were no roots remaining here, and that's mainly the idea. Okay, so what if I had something like root of 4 minus x plus 1 squared? So recall that in the previous problem I had x squared here. Now I'm putting x plus 1 squared. So how does that change the problem? Well, in this case, what we're going to do is first we're going to substitute y is equal to x plus 1, and then dy would be the same as dx, and then the integral becomes integral of root of 4 minus y squared dy. And now this integral is exactly the same as the integral in the previous example, so we proceed by substituting 2 sine theta for y. Now instead of doing that, we could have done the following. So here, instead of replacing x plus 1 by y and then do the trig substitution, we could also just directly do a trig substitution. So I can take x plus 1 to be 2 plus sine theta, so that dx is still 2 cosine theta d theta, and then just follow the same steps as in the previous example. Okay, so the next problem that we want to tackle is this integral of the root of 3 minus 2x minus x squared. So here we have the root of 3 minus 2x minus x squared. So I see that we have a quadratic inside the root, and so how do I tackle this? Well, let me first remind you that whenever you have a quadratic function, you can always rewrite this as by completing the square as a times x minus h squared plus k, and then h and k would be the vertex of this parabola. So remember, a quadratic function, the graph of that is a parabola, and hk here would be the vertex. So this is the idea of completing the square. So how do I complete the square? So I have this integrand 3 minus 2x minus x squared, and so notice that when you complete the square, the leading coefficient a is what I have here. So when I complete this square, I'm going to have the leading coefficient, that is the coefficient of x squared, which is -1 here, and times x minus the x coordinate of the vertex squared plus the y coordinate of the vertex. And so now I want to rewrite this quadratic in this standard form by completing the square, right? So basically then what I have to do is find h and k. And one way to do it is we just FOIL x minus h squared, which is x squared minus 2xh plus h squared. And then I'm going to multiply out by the negative, so I get 3 minus 2x minus x squared here, and then I have minus x squared plus 2xh minus h squared plus k. Okay, so on both sides I have quadratic functions, so they must have the same coefficients. So notice that the coefficients of the two squared terms are the same. Now the coefficient of x here is -2, and the coefficient of x here is -2, and the coefficient of x here is 2h. So I know that 2h has to be -2, and the constant 3 here must match the constant -h squared plus k. So -h squared plus k should be 3. So from here I see that h has to be -1, and if h is -1, if I plug in -1 here, I'm going to get -1 squared, which would be 1 again, so I get -1, so k would be 4. So what we have found then is that h is -1 and k is 4. So this parabola is -1 times x minus h squared plus k. We found h to be -1. So if I plug in -1 here, I'm going to get x plus 1. And if I plug in 4, I'm going to get a 4. So at the end, what I'm getting is this quadratic is -1 times x plus 1 squared plus 4, which I'm going to rewrite as 4 minus x plus 1 squared. Okay, so after completing the square, we are able to rewrite the quadratic inside the root as 4 minus x plus 1 squared. So the idea is that, okay, so then we substitute 3 minus 2x minus x squared by 4 minus x plus 1 squared. And if you recall, this is exactly the same integrand that I had here. So then what substitution do I do? Well, the substitution that I make here is that x plus 1 is the root of 4, which is 2 sine theta. So that's the substitution that we make, and then we proceed just like we did in the first problem that I completely solved. All right, so let's now say that we want to find the indefinite integral of the function root of a squared plus x squared dx. So here a is a fixed constant. All right, so to do this, we're going to make the following substitution. So in this case, the substitution that I suggested was that you replace x by a times tangent of theta. So if x is a tangent of theta, then dx would be a times the derivative of tangent is secant squared of theta d theta. So that's what we're going to substitute. So x is a tangent of theta, and then dx is a secant squared of theta d theta. Now notice that what I get then is a squared plus a squared tangent squared of theta times a secant squared of theta. Now here we can factor out a squared, and if I do that, I get 1 plus tangent squared of theta. Now the 1 plus tangent squared of theta, that's the same as secant squared of theta, and so we get root of a squared times secant squared of theta, and finally root of a squared is so we get root of a squared times root of secant squared of theta times a secant squared of theta d theta. Now root of a squared is just the absolute value of a. Root of secant squared of theta is root of secant squared of theta would be absolute value of secant of theta. And so notice that the absolute value, okay, so I think I'm missing something here. Let me erase this. So what are we getting? So first of all, the absolute value of secant theta is the same as secant theta here, because secant theta is positive. And the reason is when we made the substitution that x is a tangent of theta, we are assuming that theta is between negative pi over 2 and positive pi over 2. So theta is in the first or the fourth quadrant, where cosine and therefore secant would be positive. So because of that, the absolute value of secant theta is the same as secant theta. And I have the absolute value of a here. But now the absolute value of a and a, when we multiply them, we are going to get a squared, and then secant theta times secant squared of theta is just secant cubed of theta. Okay, so let me take a breath here. So again, after we substituted a tangent of theta, we substituted a tangent of theta, and then we kept simplifying that, and at some point we got this the root of a squared times secant squared of theta, and that we can write as root of a squared root of secant squared of theta. And root of a squared is just a, assuming that a is positive. We're going to assume that a is positive, and root of secant squared of theta is absolute value of secant of theta, but because theta is between negative pi over 2 and pi over 2, then secant theta is non-negative positive there, so we can say the absolute value of secant theta is secant theta, and then we get a squared secant cubed of theta as the integrand. Now we can take the a squared outside of the integral, so then I get integral of secant cubed of theta d theta. So now it's a problem where we have to integrate secant cubed of theta. Now let me just say that the antiderivative of secant cubed of theta is half secant theta tangent theta plus half log of absolute value of secant theta plus tangent theta plus c. And so I'm going to show you the steps for finding the integral of secant cubed of theta in a second, but we have done that in section 7.2. So once I got to this antiderivative here, now I have to plug back in x. So now how do I do that? Well, I have to calculate tangent and secant, right, at theta. So recall that we took x to be a tangent of theta, so therefore tangent of theta is x over a. And tangent of theta is opposite over adjacent, so if I make a right triangle where I pick theta to be this angle, so then the opposite would be x, adjacent would be a, and then the root of, and the hypotenuse would be, by Pythagoras' theorem, would be root of a squared plus x squared. So now I can say, hey, tangent of theta is x over a, and secant of theta is the hypotenuse over the adjacent. So the secant of theta would be this root quantity divided by a. So that's what we're going to plug in. So notice that secant theta would be so I have a squared here, so secant of theta would be the root of a squared plus x squared divided by a. Now you're not seeing that a because okay, so maybe I should write okay, so I'm looking at the half secant of theta tangent of theta, right? So half secant theta tangent theta, and so here I am plugging in root of a squared plus x squared over a. Tangent is x over a, right? So notice that I have a squared in the denominator, so when I multiply by the a squared, the a's in the denominator will go away. So that's why I'm getting only half x root of a squared plus x squared for the first term. Similarly, for the second term, I have to plug in. So for the second term, right here, so I'm just calculating the second term here. So this would be half ln, and then this would be a squared plus x squared over a plus x over a, like this. And we can rewrite this. So let me find some space here. So this we can rewrite as half of ln of x plus root of a squared plus x squared divided by a, by combining the two fractions. And okay, so the quantity in the numerator is actually positive here, because the root of a squared plus x squared is going to be bigger than x. So no matter what x is, it is going to be positive. And we are going to assume that a is positive. So then this is the same as ln of x plus root of a squared plus x squared divided by a, which we can rewrite as half, and then ln of x plus root of a squared plus x squared minus half ln of a. So by using one of the log properties, we can do this. So notice that that's what I have. That's what I have here. The a squared. So half ln of x plus root of x a squared plus x squared. That's what we got here. And the a squared is coming from the a squared outside here. And so you might say, hey, where did the ln of a go? Well, half of ln of a, that's just a constant. So because I'm adding a general constant here, I don't have to write this this half of ln of a. So again, this is just a constant. So that's why the antiderivative is simply that. So this is the final answer. Okay, so let me now go ahead and show you how the integral of secant cubed is given by this. Well, it's going to be a bit of work because it's going to involve the integration by parts. So the first thing we need to do here is rewrite secant cubed of theta. So the goal here is to evaluate the integral of secant cubed of theta. We rewrite that as secant theta times secant squared of theta d theta. We're going to take u to be secant theta and dv to be secant squared of theta d theta. And then du would be secant theta tangent theta d theta. And v would be tangent of theta. So if dv is secant squared, so the antiderivative of that is tangent. So by using the integration by parts, then we get uv, which is secant tangent, minus v du, minus the integral of v du. So it's going to be v times v du. So v times du here. So that's going to give you secant times tangent squared of theta d theta. Okay, so now we have this. We're going to rewrite tangent squared by secant squared minus 1. And so tangent squared is the same as secant squared minus 1. So then we get secant cubed minus secant of theta here. And then we get secant theta tangent theta minus secant integral of secant cubed of theta, and then plus integral of secant theta. Alright, so then at the end we are getting an integral of secant cubed of theta d theta is equal to secant theta tangent theta minus the integral of secant cubed of theta d theta plus the integral of secant theta d theta. Alright, so you might say, okay, we started with secant cubed, but we ended up with secant cubed again. What's the point? Well, we can now take this integral of secant cubed to the left hand side. So if we do that, we're going to get 2 integral of secant cubed of theta d theta is equal to secant theta plus secant theta times tangent theta plus the integral of secant theta d theta. So then the integral of secant cubed of theta d theta would be half of secant theta tangent theta plus half of the integral of secant theta d theta. And you must recall the integral of secant theta from 7.2 is ln of absolute value of secant theta plus tangent of theta. So integral of secant cubed of theta d theta is half of secant theta tangent theta plus half of ln of absolute value of secant theta plus tangent theta plus c. Okay, so that's how you calculate the integral of secant cubed of theta. So finally, let me end up by saying that we have just calculated that the integral of root of a squared plus x squared dx is equal to half of x root of a squared plus x squared plus half of a squared ln of x plus root of a squared plus x squared plus c. Now, the integral of root of a squared minus x squared, well, that's going to be half x root of a squared minus x squared plus half a squared sine inverse of x over a plus c. And finally, the integral of the root of x squared minus a squared would be half x root of x squared minus a squared minus half a squared ln of absolute value of x plus root of x squared minus a squared plus c. So we computed the first one, but the two others we didn't, but you can compute them in a very similar way. Okay, so I'm going to end this discussion on trig substitution here, and if you have any questions, let me know.